As we continue to look at RC time constants, again, remember we talked that RC time constant is a one-time constant. It takes 5 time constants for something to fully charge up, at least to the point for which we really matter about it. Because if we're thinking about it as being a mathematician or a physicist, does it ever get to be fully charged? Well, we can all say and agree no. However, remember this, we're talking about the 80 yards and punt. We're going to take it at 5 time constants. All right. We know that the inductance divided by the resistance is going to give us a one-time constant for that inductor for the current to do that same type of a charge station, right, at 63%. And again, this is the voltage. We're talking about the current here. And that the opposites are happening here. The voltage is going to drop, and here the current is going to drop on that capacitor over 5 time constants, and across the inductor over 5 time constants. All right. So we can do quite a few of the same things from a RC time constant to the LR, or we call it L over R time constant. And we could say what type of RC is needed for, let's say, 1 second time delay. If we knew that R was equal to let's say 1.5 k ohms, okay? And all we have to do now is divide that into 1 second, and we would find out what type of capacitance that we would need to do that, right? We would say that to know what type of capacitance is needed for 1 second divided by 1.5 k ohms, all right? We would know what type of a circuit would then give us a 1 second delay per time constant, which is an actual 5 second overall delay if we go to maximum. If we wanted to have the same thing for the inductance, I'm just putting that in there just to make sure it's clear. And if I had 1.5 k ohms as my R, I would say that L is equal to now 1 second times 1.5 k ohms. And I want you to look at this. That's the inductance that would be needed to create a 1 second delay, right? To make a 5 second delay, we just have to wave 5 times. Look at this. This is a large number, 1.5 K. Now we're talking about henries at this point, right? 1 times 1.5 K henries, L is equal to 1.5 K henries. This is massive. This is a very, very, very big inductor. I couldn't exactly say how big. We'd have to look it up. We can actually calculate it, obviously, right? Because we could say the number of turns times delta is over delta current. We can actually figure out what we want for, again, that number of turns and everything else, and figure out what the permittivity and permeability of everything that we need in number of current. So, I mean, there's all sorts of ways of figuring this out, or we can just go look one up on the net. But this is going to be really, really big. Too big. In fact, if we want to put it anywhere, we're going to use the RC time constant.